Good morning, everyone. Welcome to my session today. I'm Lance Gooden. I teach Calculus 3 at Johnston Community College, and that's in Smithfield, North Carolina, just about 40 minutes so from the city of Raleigh. I'm also the department chair for curriculum math department and engineering, and oversee physics, computer science, and some other disciplines as well. So today my talk is on enhance the faculty experience and skills and using Maple in the 21st century classroom. So just a bit of outline of the presentation today. Just focus on the transformational teaching, talk a bit about impact, some Maple applications that I've used primarily in my Calculus 3 class, and so talk a bit about support from what I've experienced and some changes that have occurred at our institution and at state level, and some faculty and student testimonies, and do have reference at the end as well. So I wanted to preface this talk by quoting just something from Adriana Kazar. It's a book on how colleges change, and this kind of came to mind kind of the last minute. That was from our roundtable conversation yesterday, and the idea behind that is a theory centered around second order change. And the reason I want to mention this is that when we think about where we are with the use of Maple and how we want to be able to implement this across, just implement this globally and for it to be more impactful, because Kazar essentially says this is really more of a second order change, which is very difficult to make, and specifically this is around sense making and the ideas behind changing an individual's mindset. So I want to start with this quote from George Couros, which to me is a reminder of how to truly achieve transformational teaching using technology in the classroom. And Couros says that technology will not replace great teachers, but in the hands of great teachers, this can be transformational. So I work with a group of really highly motivated and skilled faculty at Johnston Community College. I wanted to take the time to share the team. They had asked me to share this picture when they were excited that I got the opportunity to come here to Canada, and just say that collectively, they have great depth of knowledge and content pedagogy, and really have done a lot in terms of where we are in the use of Maple in our institution. So essentially we've been using Maple since 2009, and until now, we've grown significantly. I have essentially been like the go-to person for Maple, but I do want to share a lot in terms of the challenges I've had implementing Maple across the board, and really think to some degree one of the reasons why I'm here as well, and maybe all of us are actually here. So a lot of what we'll talk about today may not necessarily be directed towards you, I don't think, but it's really how we collectively can get the message across to be more impactful, globally. So let me start by talking about technology integration and what this means in our mathematical classroom. Essentially, this is challenging for novice users. And when you think about Maple and excuse me, and its intuitive, clickable user interface, this allows for the transition to be seamless. And to us it has been, but it does pose a challenge for many users. So when we think about using the clickable features of Maple, for calculus instructors, they have the ability to present concepts, through what is called the registers of semiotic representation. And this is something that was shared when I initially submitted my paper. So from some of the feedback, I did some research on this, and this looks at essentially way I view the way we use Maple primarily in calculus, and that's using these various types of representations. And this speaks primarily to viewing calculus analytically, numerically, and graphically. So in Calculus 1, when you think about the first exposure for a student, often, most calculus books we've used, it typically use a more rigorous approach, which is the epsilon delta proof. And when I taught Calculus 1, I kind of started more with graphical and numerical approach, then the proofs and or analytical approach. So what this demonstration shows, this is a video, and I do have some Maple files I can look at the end. It just shows some of the Maple tutor that does a analytical approach using the actual limits. And the traditional calculus instructor emphasizes that a lot. But there are a lot of challenges because do the students truly know what a limit is? Typically when they get to the indeterminate form, what we've experienced, they stop and do not go beyond that. Well, why not look at it numerically and graphically to get them to understand that it is not just input-output. We're approaching something. And when students get that in their minds, then they get a better sense of what they're doing analytically. And then they'll have a better understanding of the rigorous approach using the epsilon delta proofs. Also want to talk about is the idea behind symbol sense. So one of the things we want to think about is really some of the challenges that we encounter when we're trying to get the message across to faculty. So, Kazar also mentioned the idea behind anti-learning behavior. So in order to improve learning and how the faculty or students utilize the software, well, let's talk about some of the possible anti-learning behaviors. So this is, the idea falls around what I view in my paper as symbol sense, and essentially the awareness that one can successfully engineer symbolic representation, which expresses the verbal or graphical information needed to make progress in the problem, and the ability to engineer those expectations. And also for faculty, we think about also the ability to select possible symbolic representations of the problem, and if necessary, to have the courage first to recognize and heed one's, dissatisfaction with that choice, and second, to be resourceful in searching for a better one as a replacement. So when we think about some of those anti-learning behaviors, think about time specifically. Well, when you think about the idea of time, for a novice user, it's time consuming. So does the faculty have the time to commit to actually learning the software and utilizing it in the classroom? Because the reality is, with that learning curve, it consumes some instructional time. Also, think about trust. So the idea behind trust, from a faculty perspective, is that does the software necessarily do what they intend for it to do? But that also comes with some comfort level and expertise, right? So in order for the use of the software to be more impactful from an instructional perspective, think about the fact that you need the faculty to have a sense of trust for the software. They believe that this is exactly the tool, the best tool to enhance the learning experience in their classroom. In addition to the idea behind trust, the idea is that we have so many experiences from a classroom perspective in terms of just troubleshooting. So when you think of it behind trust, the idea is that if I'm teaching a class of 30 in calculus and there are issues, there's so many things that could go wrong, but the faculty themselves need to have a better understanding of how to address those things just on the fly. And that essentially takes time. So what I've experienced, especially with the recent launch of the Maple Companion app, that has made the use of Maple in the classroom so much more efficient, because what before the launch of the app took 15 to 30 minutes just to get someone to transcribe a problem, from a handout to Maple, now it takes, within probably 2 minutes for a class of 30. Capture the problem, send it to Maple Cloud, pull it in, and we're working. And the moment it was launched, the following Friday, I was able to use it. So that in itself, it makes the software so much more efficient, or use in the classroom so much more efficient. So those are some things that also addresses some of the anti-learning behaviors, for faculty use in the actual classroom. It's a risk. We want our faculty to be risk takers, because the idea is that there's so many unknowns when you're using Maple in the classroom as an instructor for essentially a large group. So if there's so many unknowns, so many unpredictables, then the individual themselves need to be comfortable with that and be able to address them as they come. And also, does Maple really, how does that address, enhance my quality of instruction? So, those are questions that often go through the faculty's mind before they decide to use the software. We know all the fabulous features are there because we've been using it so long, and in reality is we have very different skill set that many may not necessarily have. And what value does Maple add to my classroom? So these are some examples of some of the anti-learning behaviors I have observed from the faculty members using Maple in the classroom. So I want to talk a little bit about this particular theory. So this is the idea behind a technologically pedagogical content knowledge framework. And when you look behind the idea behind this framework, essentially looks at the pedagogical knowledge, the content knowledge experts, as well as the technology use. So the framework in itself combines, it's presented in this manner, and it's definitely something you can look at some point in time. But when we look at the intersection of the pedagogical knowledge and content knowledge and technological knowledge, then that encompasses the technological pedagogical content knowledge. And the idea behind this is important as we think about the other users or novice users to adapt to your software and be able to be effective in the classroom. So we're here because we all possess that particular knowledge and we're there. So it's not fair to assume that all other faculty members are essentially there when we think that why aren't they using the software? So the reality is this is a particular pedagogical knowledge that the faculty member needs to be able to have. So how can we use Maple to enhance that particular knowledge? And Maple is designed to do that. One of the things with faculty members is the idea is the purpose. So why use Maple? So from a faculty perspective, it's important to think about the skill sets that Maple also addresses for the student user. So when you think about what one particular skill is really the technological literacy. So something to think about is that in our state of North Carolina, we've had a huge shift in how we've implemented our math. And that's also bringing the idea of quantitative literacy for individuals to be better consumers of math. So with the approach in terms of quantitative literacy, we have kind of split from a STEM and a non-STEM pathway. Hence, the non-STEM pathway is quantitative literacy. So, my approach really at this point is, well, what about technological literacy? Is that important? Should it be? Yes, it should. And Maple addresses just that. So I've actually incorporated, goals and annual plans into my program and courses to really enhance this particular skill. So this needs to be a purpose in terms of the implementation of Maple, and it makes it more meaningful for faculty members moving forward. So one of the things, quoted by Cook and the rest is that institutions should actively develop learners' technological literacy. One, that is to produce graduates who are adaptable to the ever-changing global market. And just a bit about the definition of what it means to be technological literate, and that's the possession and understanding of technological evolution and innovation, and the ability to apply tools, equipment, ideas, processes, and materials, that is satisfactory to the solution of human needs. So, beyond this, I'll start showing you some of the things I've used in my Calculus 3 class to really enhance these particular skill sets, and things I would want faculty members to use. So when we think about the idea behind exploratory exercises, I use a lot of visualizations and animations, and we've also talked about that as well. So one in particular, this looks at just optimization for a surface. So when you think about teaching optimization on a restricted boundary, well, before I get into the applications of partial derivatives and the various 15 or 25 steps the students have to follow to accomplish this, why not be able to show what you're trying to achieve? Because there are so many elements here to consider. These are on the boundary. We're looking at also along surfaces and so many different ideas of extrema. The other is also looking at the Frenet-Serre frame, which looks at the orthonormal vectors, torsion, and curvature. Well, before I start getting to those computations, students will actually see this visualization and see that, well, something to keep in mind is the fact that we have what's an oscillating plane. So we talk about those concepts before we get into the actual calculation. So the idea is that, pedagogically or pedagogically, it's important to think about how we best utilize the software to meet the needs of the learners. So the choice of what you present first is important and impacts, what students take away from your actual courses. Storytelling, that's a great way to bring excitement and life to your classroom. So, a lot of the applications we're doing in math is essentially you're telling a story. So I brought 3 examples that I use in my classroom, and in Calculus 3, I create 3 semester projects. And, essentially I call these are actually checkpoints in the course to see, well, we've done this much work. How well do you know it? So for the first, it looks at just a application of projectile motion in space. So an object is launched above ground level. In addition to acceleration of the gravity, some of the force causes the object to drift. So in the groups, they go through lines of codes, and essentially what we produce is an animated graph of what's truly happening. Here we have that object represents the ball, it's above ground level, and then it's launched, it drifts, and then it lands in the XY plane. So have them see the end in mind. So essentially, the students would see this particular animation first, and this is actually an example of what a group submitted in my actual class. So students are able to do this at the Calculus 3 level. But this happened in phases, so there's several things that we're doing over a course of maybe, I'd say 2.5, 3 weeks before they get to this point in the actual course. So another example looks at an application of the partial derivatives and chain rule. So this is a really neat one because, again, it's from a textbook. Here's a problem. I say, well, let's bring this to life. This is an actual two particles traveling on elliptic paths. And the idea is to find what's the rate of change of the distance between the particles at a specific time. So sometimes the problems in calculus, they seem very static. And in calculus, nothing static about calculus. Everything is actually moving. It's very dynamic. So we do our very best to present it in that manner. And hence, it brings, I think, more exciting life, understanding, depth of knowledge to our actual students. And the third, this also looks at another application of the directional derivatives and gradient, which is essentially a particle moving along a surface. So again, lines of code, and essentially, I always start with an animation. This is what we're trying to achieve. Well, in order to do this, there's several things we need to learn, and students better understand the purpose of what they're learning. And these are some things I want the faculty members to be able to do to really make the learning and experience in the class much more meaningful. Making math tangible. So in my engineering program, we do a lot of 3D printing, and Maple has just great feature to be able to export some of the surfaces to STL. So some of the tables have some samples of the 3D prints we've done in class. And this is also great. This has been a great experience, excuse me, for our students as they find that, well, the math can be tangible. I've learned all this math, I've written all this code. Well, wow, this is actually a math equation. So, we have the torus, we don't have another application with it, but this is a parametric surface. We're able to use that. This particular application ties more to engineering because our students use a lot of CAD software. So while it's parameterizes circle, well, we extrude the actual circle, and the extrusions, that's important for SolidWorks, which is what we use in engineering. And this is also an application found on the web in terms of treating tumor with a bumpy sphere, they call it. But then we can actually take that equation, create the surface, export to STL, and here's a physical model of that. So those things are also meaningful to learners in the actual classroom. Finally, I look at the idea of global awareness through Maple. So when you think about what this means in terms of global awareness, this allows the students to collaborate the experiences, to foster adaptability, very effective in communication, and create problem solving, technological proficiency, and culture. So they're able to connect with users across the globe through Maple Primes. I mean, it's just fascinating. So I'm like, get in Maple Clouds, use all these features, because now you can connect with people across the globe and see how they're using Maple differently and share ideas. So these are great experiences to bring to the classroom as well. So with all that, faculty need professional development. You know, we think, oh, this is great. It's easy. I've stopped saying that because I have failed at it miserably. And that's, you know, one of the reasons, again, why I'm here, because after 10 years, and I've never used Maple prior to 2009, and, you know, my paper shared my experience, I had maybe a 5 or 10 minute tutorial, if you may call it so, from my predecessor, and she just simply said, you've got to keep using this. And it took a lot of time to get to this point. All the resources, great clickable series from Dr. Lopez. I'm like, oh my God, I'm actually here. Lopez, this is awesome. Got to get his autograph. And so it's just fascinating to actually be here, to realize that, you know, I've used just about everything, and it has worked very well for me. And I thought that I could do the same to inspire my faculty. It did not work. And many here, Karishma and Yogan, can attest to that. But, you know, thanks to the support of the support staff from Maple, we've accomplished a lot. You know, we've actually done some professional development for the faculty at Johnson Community College, and actually expanded that across to the state. Excuse me. And really, this is just a testament to how impactful, high quality professional development can be for, you know, the faculty in the actual classroom. So this is from Stephanie Hall, and, you know, Karishma and Yogi know her. These are some comments, and this is a huge accomplishment because Stephanie Hall and I started at the same time at Johnson Community College, and she's just now at this point using Maple. But thanks to what they've done implementing training for faculty, they're using Maple Bootcamp. You know, we've virtualized Maple for 4 or 5 years, and, you know, I thought getting the virtualization, you know, gives access to the students, and I thought that was a way to go, or, you know, reduce cost to some degree. Not necessarily. You know, it goes back to what it said in the beginning. It starts with the faculty. You have to inspire the faculty members, get them excited about using the software, and that can be much more impactful in terms of the use of the software across the globe. So, you know, my talk is really about inspiring, enhancing their skills, so they themselves can impart that knowledge and skills to the students, not just locally, but globally. So this is just, you know, a thank you to the team and what they've done to bring her at this point. She's now, you know, using the software in Calculus 2 religiously. I'm like, come on, you should be using it through all your sequences, linear algebra, differential equations, and they're doing great things with the software. But it's not going to come from me. It doesn't help because I'm also their supervisor. And they call me the Maple Guru, and I'm telling you, after what I've seen today, I am a novice from the presentations. Also, you know, Stephanie asked to share this because, and that's Stephanie Hall, she, from her experience, just wanted to also share how she's using Maple in the classroom, what she's experienced. So with Maple, students are relieved from the pressure of computations and are able to focus on demonstrating and understanding of concepts. She also talks about the concept consolidation. So, you know, so now's the time to start getting those who weren't believers. If you can change their mindset, you sell those stories, not the ones like, oh, I mean, not that we can't tell the story, but it didn't take much for me to realize this is it, and there's nothing else anyone can do to convince me otherwise. But what about those initially like, no, I mean, I don't want to use it, and to get them at this point. So for me, Stephanie is a success story, and I just want to say thank you again to Karishma and Yogan for that. This is a student from my Calculus 3 class, you know, based on what I've done with him up until this point, just want to share some of the experiences he has had as well. So they love not just the visualizations, but also just the steps. And it's not a cheating tool. I mean, they cannot cheat in my Calc 3 class. It's impossible to do that. Not the way I write the assignments, but I encourage them to use it. I mean, everything's built around Maple, so use the steps-out solutions. Just start mapping this back to things that you may have learned from Calc 1 or pre-algebra or college algebra, because there's a lot of transfer of knowledge. So do we expect them to remember every single thing they've learned in their prerequisite courses? Not necessarily. So it's a great tool, and certainly has been just provide a positive experience for students. I do want to do a bit of some demonstrations, but I also wanted to share this. This is kind of bringing things to a close. But here it says, it's something I wrote that with Maple in the hands of motivated and skilled faculty, teaching mathematics can be transformational. Improving the technological, pedagogical, content knowledge, and literacy of the faculty use of Maple in the 21st century math classroom will have the greatest impact, I believe, on student learning. So with that, I wanted to just switch to Maple and just show you some of the demonstrations that actually recorded on the video, because when we're here at the conference, I'll show you what else I do in Maple. So let me see if I'm able. So this is the file, which is just really Calculus 1. Initially, I said it's something that I showed the team at Johnson Community College. And again, while it's amazing, what they found it amazing, I mean, for you, it's easy to do. And it really is, but it's not fair to say that for the novice user. The idea is that it's not very clean, but the reality is I want students to be able to learn how to use Maple to create these kinds of tables and executions, but also to see truly what it means to compute a limit. So it's not necessarily input-output. We're approaching a point from different angles, and it also translates well to multivariate limits. And also graphically what that means with the animation. And it's important that the user sees that. They're approaching from left to right, so we trace along the x-axis, trace along the curve, and the animation feature really does a good job to show that for students. But much of the others are in Calculus 3. So this is a great tool. Started out with so many skills in the classroom, because the students, when we give them this project, they actually take the project and then enhance the project to say, well, if I have a square boundary and that creates a square prism and it projects upwards or extruded upwards or downwards to a surface and slices the surface, what does that mean in terms of extremis? So, much of the line commands are applying the partial derivatives, finding critical points. But to do that, we have to look at critical points on the vertices, critical points along the traces, and then look inside the boundary in terms of an extrema that may lie above the highest point or below the lowest point. So several things to consider, but they need some geometric representation to say, well, this is essentially what I'm trying to do, so now let's go through the steps. And that's the approach I typically take in my Calc 3 course. And this is the one involved in the particles moving along an elliptic path. So as I said, you can bring math alive by looking at the problem. With Maple, you can do it. This is exactly what it wants us to do, but it's telling a story. And then we can actually have things animated using Maple. One of the things I want to show that not necessarily was in the slides, and this was a simple code to extrude. I found out a few days ago from Maple Primes that there's code now to add thickness to your quadric surfaces. So what I'm going to do when I get back to Johnston in North Carolina is I've now, as I've already tried it, late night for a presentation, but I'm now going to add thickness to all my quadric surfaces and 3D print them. So I was like, oh, that's awesome, great. So they'll have, that object in their hands, and they themselves will be able to create that and 3D print it. One of the last projects, 2 minutes over. I'll stop now for questions in a minute, but one of the things I've been working on is also this application for, let me go back a bit to show what students typically see, involving triple integration. So this is triple integration in spherical coordinates, and what this allows them to do, what I consider is essentially a disk that form, and this allows them to better understand the limits of integration, but this particular application allows them to adjust all the limits to see the really geometric representation of integration. So when you think about single, double, triple, with an integrand of 1, you can take any single integral and write a triple integral with it, because it's geometry. So the reality is that with a triple integral of 1, it's just base area times height. If the height is 1 times the base area, it doesn't change anything. And that's the understanding I want them to get from the triple integration. And once they understand setting up the limits, then they can compute the integral. So the idea is that don't just compute an integral when the limits are incorrect. It may lead to something that's impossible for you to integrate. So we add these features for the various types of visualizations. Right? I'll stop here for any questions that you may have. Thank you for your time. Yes. Awesome.
You mentioned the faculty, you thought you went in with an open mind, thinking that they would embrace this. What would you say the top 3 reasons are that they don't?
The learning curve, that was great. That was really one of the greatest in terms of learning curve, because it takes time. So for them to be able to get accustomed to what's there and how to best use the tools in their classrooms. 2, there are some that didn't believe it would change anything. I mean, if the faculty just doesn't believe in utilizing technology, that's even a greater challenge. So it's kind of really changing that mindset. And 3, fundamentally believe that math should not be taught that way. So remember when first kind of presented some of the applications to Stephanie Hall, I was like, why would I want my students to see the stepped out solutions in computing the limit or derivative when those are some of the first things they're doing in Calculus 1? Well, why not? And it took from 2014 until now to get her to that point. Yes.
You mentioned at the beginning or at some point during the presentation that you kind of got started with your Maple journey in around 2009.
Yes.
What was your start? Was it an epiphany? Were you told to use it? Like what got you down the path?
Yes, it was the predecessor who retired, and she was teaching Calc 3, and she knew I was going to take over the course, and she sat down with me really 5 to 10 minutes using Maple 9, using 1D actually, and just said, these are some things Maple can do. It's great. You should use it. And that's all it took for me. And from there, I just devoted a lot of time just using it. And as users, there's some just have the ability and intuitiveness to just get the software and use it. And I think I am, and because of how I teach and view things, that has enhanced my teaching tremendously. Yes?
I think the 3D printing is really a fun thing and an easy way to capture a lot of student interest.
Yes.
And mathematically, the books all talk about oriented surfaces.
Yes.
And what I had to learn about 3D printing is you don't print a surface.
No.
You have to print a solid.
Exactly.
So that's why you said adding thickness
Yes.
is so important.
Yes.
And that's what when it prints that thing, it has to know which way is the inside to fill, which way is the outside to not fill.
Exactly.
And if that exporting doesn't get all the orientations right,
yes.
you get some interesting objects.
Absolutely.
and it's all my fault. That I didn't pay attention to orientation of the surfaces and check those things. And the software will do all that for you. But those are things that I taught those things for decades.
Yes.
And who came up why? And then when I saw the 3D printing, it's like, oh, that's where it matters. And
yes.
And the students pick up on it very quickly.
Yes, they do.
So that's almost a killer app that captures a lot of students' interest. The things that they can, if I can do this, then what else can I do with it? And I think that, then they will pay attention, and they will do some of the things they details have to pay attention to, and so I think that's a really nice thing to be able to design things on a Maple there, and then just export it and watch it print.
Yes, and we even talk more about the the slicing software, because that's a lot of, our chapter 3 or 13 in terms of the contour plots and level surfaces and really partial derivatives in terms of the printer tips and how it moves across the surface. So I actually run 3D printers in my Calc 3 classroom. I send a print when I'm teaching those applications of partial derivatives. Yes, Dr. Lopez.
What kind of support did you get from the administration?
So I am the administration. and financially, so
You gotta go to somebody for money, right?
so
So there's somebody above you.
yes, there is, and I got the money. So they're in full support of technology. So my supervisor, Dawn Dixon, she's highly supportive in terms of technology use in the classroom. So in terms of that support, there are no issues there. So the funding has never been an issue for our institution. It's then is really how to get the faculty to use it. So unfortunately, I don't have that. I haven't had that issue at all.
What happened at Rose-Hulman was I started using it in the classroom.
Yes.
And it got to a point where the department had to make a decision. Either everybody was gonna use it or nobody was gonna use it. And the department came to the conclusion that everybody would use it. So it became a mandate on the department.
Mm-hmm.
Okay, and I'm wondering, what would happen in your department if it were a mandate? You have to use it. See, is a minimal usage that everybody has to agree to.
And it goes back to the idea behind change or theories behind change. I thought about that, and one step was to write that in the curriculum. I think you talked about that yesterday in the roundtable session. So it's now utilization of Maple, specifically a computer algebra system, is a skill, a 21st century skill required for all our calculus courses. So it's there. How they use it varies across courses, and it takes time to get there. So if I were to mandate that initially, then really the way our community college system work, the faculty would not take that very well, and that in itself could lead to loss of funding, because they would have every reason to show that we're wasting our money, and they could do that because of utilization. So I chose not to take that approach and just try to call on the Maple team to really provide some expert support for the faculty and have them to understand what's out there and how to best use it in their classrooms.
I think Robert's example is a little bit different.
Yes.
The administration didn't decide. Right?
Mhm.
Faculty got together and decided. Right?
Okay.
Am I right, Robert?
Yeah.
And they bought in and realized if we're gonna make a choice.
Yes.
Either none of us are gonna do it or we're all gonna do it. And they may have said, I'm not real comfortable with this myself, but I realize this is in the best interest of our students and our institution.
Mm-hmm.
So it wasn't dictated by the chair.
Okay.
The chair said you gotta make a decision. Right? Now, you gotta be
Yeah,
careful.
yeah.
Be careful what decisions you ask them to make.
Yes.
You
So.
gotta get them, I think that's what I heard in Robert's example there was, you gotta get them to realize that, yeah, we gotta suck it up and together we can do it.
Okay.
But not to force you to make the decision and say, not crack the whip and
Yeah.
say you're gonna do this.
The thing that really pushed the department to have to make a decision was there were three of us that were using Maple, so those calculus classes were distinct from the other calculus
Oh,
classes.
okay.
So now you have this dichotomy.
Yes.
And the friction that created was what forced the department to confront all or none.
Okay.
And even though there were a couple old guys that retired eventually because they were not comfortable with
Yes.
change,
Yeah.
the department accepted the all.
Oh, okay.
So one ploy is to have these classes use Maple, these classes don't. Now you have students wanting to go from one to the other, and this creates havoc for administration.
Oh.
And now you decide what are we
Interesting.
going to do. Right? Now, I'm
Okay.
not saying that you should do that. I will tell walking down the hall with one of the full professors. I had just gotten tenure. And I'm walking down the hall, and he looks in at the mess. He looks back at me. He looks back at the mess. He looks back at me. And he says, "You know, Lopez, it's a good thing you got tenure now."
Well, excellent. Well, thank you, definitely. Certainly, I'm open to ideas, and just really want to not just improve or increase the usage of faculty at the college, but really across the state of North Carolina, because there's so much change in terms of math and engineering, and so many more really ought to be using it. So definitely open to ideas and suggestions and ways we can be more impactful there. Yes. Any other questions? All right. Oh, sorry.
Oh, we have dinner, okay.
Oh,
I'll come find you later, man.
oh, okay. It's great for shaking hands. It's fine. But thank. All right, thank you.
Yeah, and I'm happy too, but,
Uh,
well, we'll come, we'll
Oh,
chat.
okay, that's fine. All right, thank you very much.